We continue our exploration of the mathematical underpinnings for this course by looking at functions and relations. A function is simply a mapping that takes an input and maps it to an output. The familiar notation shown here has a function named f that maps the input a to the output b. The set of all possible inputs to the function is the domain of the function, and the function must be defined for every member of the domain. In this course, we're going to work strictly with single-valued functions, which means that functions cannot map the same input to multiple outputs. An example of a multi-valued function would be the square root function, where the square root of 9 can map to either 3 or -3. However, while single-valued functions can't map one input to multiple outputs, they can map multiple inputs to the same output. Think of the absolute value function, where the input values 3 and -3 both map to the output value 3. The possible outcomes are contained in a set known as the range of the function, and there's no requirement that all elements of the range have to have a mapping from some input in the domain to that element in the output. For example, if the domain of our absolute value function is the set of integers, then we can consider the range of it to be the integers as well, even though none of the negative integers in the range are mapped to from this domain. So let's look graphically at what a function is, and also a couple of special kinds of functions that will be very useful to us in this course. In general, a function maps values from the domain to the range, and as we can see in this graphic, every value in the domain must map to exactly one value in the range, but we are allowed to have multiple values in the domain, in this case a and c, that both map to the value r. We can also have values in the range, a and b in this case, that do not map to any value from the domain. This is our generic run-of-the-mill function. One special function we'll use is the surjective function, also known as an onto function. What this means is that the function reaches every element in the range from the domain, though we still allow a given range element to be mapped to by multiple domain elements. An example of this would be our absolute value function, in which the domain is still a set of integers, but the range is restricted to being the natural numbers unioned with 0, the set sometimes called the whole numbers. Injective functions, also called one-to-one functions, on the other hand, require that each element in the domain map to a distinct element in the range. However, here we allow there to be additional elements in the range that are unreachable from the domain. If we combine these two concepts so that we have a function that is both injective and surjective, we end up with what we call a bijective function, also known as a one-to-one and on-to function. Another name that we will use for this kind of function is a correspondence. As you can surmise from the diagram, the number of elements in the domain is exactly equal to the number of elements in the range, and this is a property that we're going to find extremely useful in the latter part of this course. A little terminology that we'll see from time to time in the textbook is a k-ary function. It simply means a function whose input is a k-tuple. If k is equal to 1, the function is known as a unary function and just takes a single input. Common examples are arithmetic and logical negation. If k is equal to 2, the function is known as a binary function, and most arithmetic and logical functions fall into that category. When we have a binary function, we often write it using what's called infix notation, which is the notation that you've been using probably since 2nd or 3rd grade, where we write a symbol that represents the function in between the two arguments of the function. Remembering that the arguments are, in general, a sequence, we write the first element in the sequence before the function name and the second element after it. If the function is commutative, such as addition and multiplication, this doesn't really matter, but for other operators, like subtraction and division, it does. Now let's consider another special function, the predicate. This is merely a function whose range consists of just two values, namely true and false. These are used all the time in programming, and you're all actually quite familiar with them. The relational operators, such as less than, are Examples of predicates. In programming, whenever you use an if or a while statement, the test expression is a predicate since it's an expression that evaluates to either true or false. In mathematics, this is also known as a property. Because we only have two elements in the range, we can actually define this function by simply identifying which arguments in the domain map to true, because we know that all of the others must map to false. A relation is a predicate in which the domain is a set of k-tuples. If it's a binary relation, its domain is a set of ordered pairs. As before, we can then define this relation by listing all instances for which A, R, B is true, where R is just the name of the function. Don't let this be confusing. Normally, if we see A less than B, we interpret this as a question having one of two answers, true or false. We can still use it that way. But when we are defining a relation, if we include A less than B for particular values of A and B, we are declaring that A or B, in this case A less than B, is true. The context in which you see the expression should make it clear which interpretation is intended. Binary relations fall into some useful categories. They are reflexive if, for every element in the domain, it is true that the function is true when that element is used as both arguments. A relation like less than or equal to is reflexive. A relation is symmetric if the order of the arguments doesn't matter, which means that if xry is true, then yrx must also be true. An example of a symmetric function would be the logical OR function. A relation is transitive if having both xry and yrz being true implies that xrz is true. An example of this is the less than relation, where if x is less than y and y is less than z, we can assert that x is less than z. If a relation happens to be all three of these, it is known as an equivalence relation, and it implies that if x or y is true, that x and y are equivalent in some fashion.